So here's an interesting observation. There was somebody who had an intern who's less than 20, and one thing they were not comfortable doing was calling people on the telephone. And because I was thinking if you had to make a dinner reservation and you had to call somebody and talk to somebody on the phone, or if you would just use some app to make the reservations, which would you choose, right? You probably use the app. We tend to avoid some human interaction that was necessary many years ago, which personally made me feel uncomfortable because I was not an outgoing person. So I probably would prefer to use an app to make a reservation as well, even though I probably would. I mean, around here, it's probably not something that you could do very well, but it's interesting, just things that are something that we would, as older people, would not consider to be that unusual, but because of the way technology is today, you end up having these situations. So that was an interesting observation. Here's another observation. So I've been telling you about watching these travel vlogs and how you go from traveling for a year. You go like, okay, I'm going to travel for a year. I sell all my stuff. I got $20,000. We're going to travel on the cheap. And then you're like, okay, maybe we could do this full time. This would be a business. Okay. So then they get into it, and then initially they see their viewers go up, and they're like, oh yeah, we can do this. We can do this. And then they get to a point where things are not as your expectations. It's kind of like going to college and you think, I have this dream job, and then you get out of college with debt and your job is not paying enough and it's not as wonderful as you think it was going to be, and then you're kind of in a funk. This stinks. So this one couple, I told you the three that I had been looking at. So they had this video. It's kind of like, this is our current situation. So what they've gotten to is this point where they're barely making enough to keep going. Okay, they're barely making it, and you're putting a lot of effort into these videos, and then you tie your self-worth to the number of views you get from both a financial perspective and a personal perspective. And it turns out that for some reason, viewership in January, February, March goes down. So they get, before Christmas. I don't know why people are watching more videos before Christmas, but and then you also, it's kind of like a lot of things. You start to project out into the future. This is how I'm doing, so I'll keep doing this well, or we'll do better. And then you have this drop off. It's not just in videos; it's in businesses per se. If you don't have any cushion, or if you don't have any strategy. So that's one thing these people were dealing with. It's kind of sad because the girl and the couple, I've watched enough videos to know, I could tell her she was about to cry. She was getting all teary-eyed because of getting emotional about the whole thing. So then you run into this thing. You're building this YouTube channel, and you're trying to get enough revenue to keep going. So then you take on some sponsorships, but then when you have sponsorships, it becomes less authentic. And then you struggle with the case of, is the channel about travel or is it about the couple? If it becomes too much personality driven, then do people get bored with it? I mean, I don't watch. It's kind of new to me. You guys probably do more of that than I do, but it's interesting. Not just, you just look at it from I originally was searching for places. I was searching what to do in Cologne, Germany. That's how I kind of ran into this couple, and I thought, oh, this is kind of cool, and I'm starting watching them, and then I'm like, oh, I'm watch some other ones, and but like I always do, I overthink things. So um, so yeah, it's kind of interesting because you balance that, but there you get to a point, whether it's a business or it's this particular channel. I guess I appreciate it more because it's more accessible. if some guy has a donut shop or something like that, I'm not going to experience this guy's struggles from day to day. But now you get this personal investment in this couple, and so they so they're trying to get sponsorships, but then again, how much is that influencing their authenticity? So you run into this conundrum. Is that a word? Conundrum about how do you do it? And then the other thing too, it's like with video. When our kids were young was when they first started out with VCR recorders. So everybody was there with their cameras, looking around, taking pictures of their kids doing anything. And we were too cheap to buy one. Not that we couldn't afford one, we just were too cheap. So we never did buy a video camera. Now, 20 years later, you look back, do I regret not taking videos? Not really. Did people who were too busy looking through the camera and not get enough out of the experience that their kids were going through, and they were too busy just filming them to watch later, and then the VCR technology disappears, and your player doesn't work anymore, and you don't watch them anyway. It's so the same thing with the travel. If you get this travel business, and you're trying to get new content, so you don't stay someplace very long, and the time that you're there, you're taking pictures, and you're not really experiencing it. Is it really authentic anyway? So anyway, things to think about. Don't always look at this. I think it's interesting to go dig into something a little more deeply. Don't just look at the surface of things. Okay. So what we've done so far is we looked at the force on a moving charge. So you've already gotten this all written down. Force on a moving charge is equal to the charge times the speed, the velocity times the magnetic field, and it depends upon the orientation of the magnetic field with the velocity to tell you how much you get out of how much force you get. And if you have a wire, which is a bunch of moving charges contained in a circular conductor, usually circular, doesn't have to be circular, but the force on the wire is the current times the magnetic field times the length of the wire. And if we have a loop that's made out of wire, the torque is the current times the magnetic field times the area of the loop. And again, it depends upon the orientation of the loop as far as whether you get zero torque or you get the maximum torque. Okay, so the question is, next question is, what about the magnetic field created by moving charged particles? So we're going to go back, but instead of talking about the force on a moving charged particle, we're going to talk about what is the magnetic field created by moving charged particles. But before we do that, we're going to answer that question today. Before we do that, we're going to go back and look at Coulomb's law and electric fields. So the expression for the electric field in non-vector form says the electric field at a point in space is equal to Coulomb's constant, 8.99 times 10 to the ninth, times the charge in coulombs of the charge that you're trying to find the electric field around, divided by the distance between the charge location and the point in space that you're trying to figure out the electric field. So that's how you calculate the electric field. And then if you have multiple charged particles, you calculate the electric field due to each charged particle and add those fields together to get the total field. It's called principle of superposition. But the electric field comes from Coulomb's law, which talks about the force. Now, we don't really talk about forces per se the same way in magnetic fields, but we do talk about magnetic fields. So if you were a scientist and you were trying to figure out what is the relationship between the magnetic field created by a moving charge and points in space around that moving charge particle, you might come and say, well, maybe it's something like the same thing that we got looking at in terms of the electric field. Maybe it's of some form similar to this. So you run some experiments that kind of try to figure that particular question out. which we'll get to in a second. One more thing though, before we get to that, is I want to talk about the concept of what a unit vector is. So, a vector is a quantity that has both magnitude and direction. So I have a vector which has a x component of 4 units and a y component of 5 units. And if you use the Pythagorean theorem, you find that the magnitude of the vector is the square root of 41. And it's pointed to the upper right corner. Now, what a unit vector is a vector that has a length 1, but is pointed in the same direction as the original vector. So the square root of 41 is going to be around 6, a little over 6 units. So if I take this vector and I decrease the length by about a factor of 6, which I'm just going to eyeball it here. So let's say that. Hopefully if I took this and I put it tip to tail all the way along here, I'd get 6 point whatever the square root of 41 is. So the unit vector is this little vector here. I'm going to use a little u for that, and I'm going to use an arrow. So the unit vector has the same direction as the vector p, and to get the unit vector, you take the vector p and you divide by the length of the vector p. So this is the two vertical lines mean the magnitude. So in this case, the magnitude of vector p is equal to the square root of 41. And in vector notation, I'd say the unit vector was equal to, and for our particular example, would be 4 the x component of the vector divided by the magnitude, the length of the vector, times this unit vector in the x direction plus 5 divided by the square root of 41 in the y direction. This is just a way of representing. And if I did the magnitude of u, it would turn out to be 1. So the length of u is 1 unit. The length of p is square root of 41 units. But the u vector, if I look at the vector, this vector u is going to have the same direction. So same direction, unit length. Okay. Now here's a very complicated drawing that I got out of the textbook, your textbook, and that's why I brought this stuff in to try to explain what's going to happen here. So what we have is we have this moving particle. So you can imagine it moving, and we've taken a picture here, and we know what the velocity. So the velocity is going to be going this way. And there's a vector associated with that velocity. It's going to be a vector that's pointing this way, and the length is whatever the speed of this charged particle is. Okay. Now here's some point out in space, and I want to know what is at that instant of time, what is the magnetic field at this point due to this moving charged particle. So the particle has a velocity vector this way. There's also a vector that goes from the center of the charged particle to that point in space. So there's this vector here. And if I move, wherever I move around, the velocity vector is always this way. But depending upon where I go around here, whether I go further away or closer, my vector, where my fingers are, gets shorter or longer. So this is here's the charged particle, here's the velocity vector, and then you have the vector from the charged particle to some point in space p. And at that point p, there is a magnetic field vector. Now what this is doing is it's showing different magnetic field vectors due to this moving charged particle at different points in space. And the ones that are closest, the ones that have the smallest distance between the charged particle and the point in space, have the larger magnitude. So the further away you get, the magnitude of the magnetic field vector gets less. So these two are shorter. This one's longer because it's the closest. And then there's this angle between, this angle phi, which is the angle between the velocity vector and the position vector from the charged particle to the point in space. And it turns out that if you do experiments, that let me put this on one page, the magnetic field due to a point charge with constant velocity, and it's a vector, is equal to this new constant called mu zero, not epsilon zero, but mu zero, divided by 4 pi. So this is kind of like K times the charge. The charge is in coulombs, and it is a scalar. The next thing you have is the velocity vector. So you can see a little arrow on the top. Then you have the distance, and this is a scalar. This is the distance between the point here and the point in space. So it would be, I can't put it in the middle, but you can imagine this is going to be r. If I take this around and, this r is constant as I rotate this thing around. So that's a scalar. And this is what's called a unit vector in the direction from, so unit vector from the point charge towards where the field is measured. So let's say I want to measure the field here. The direction from the point charge to the place I'm trying to figure out the magnetic field is out here. The unit vector would be a shorter vector, possibly. It could be longer depending upon how close you are, but it's going to be a vector that's 1 unit in length, but has the same direction as this position vector. And the way you get the unit vector is you take this vector, x, y, z in this case, location, and divide by the length of the vector, and that gives you the unit vector. So what this does is it provides information about the direction or the position of the point in space relative to the point charge. And then you do this thing called a cross product, and the cross product is the right-hand rule. It's a mathematical way of representing the right-hand rule. And what happens is, not mathematically, but you have the velocity vector going this way, and you curl your fingers toward, well, it's kind of, before we were looking at the force, here we're trying to figure out the magnetic field. So there's an equivalent type of right-hand rule. So anyway, the bottom line is this takes into account the right-hand rule kind of information. I'm just going to demonstrate how you get a cross product. It's not that hard mathematically. So I think it's worth at least demonstrating it. So let's say the velocity vector consists of different, and we're going to use 3 dimensions just to make it general. So you'll have, v sub x, the x component, multiplied by this vector in the x direction. You'll have v sub y times, which is your y component of velocity, multiplied by this unit vector in the y direction, and you have v sub z, which is the velocity in the z direction times the unit vector. So this is just a way of representing a vector in the 3 components. And then you have this unit vector. So we'll have some r sub x times I plus r sub y times j plus r sub z times k. And the magnitude of the unit vector is 1. That means r sub x squared, oops, let me write this out. So if I take these separate components, r sub x and I square it, and I take r sub y and I square it, and take r sub z and I square it, and take the square root, that ends up being 1. And again, all this does is it just tells you the direction, the relative direction of this point in space relative to the direction of the velocity. So if you take the velocity vector and you cross it with the unit vector, you guys haven't had matrices before, but I'm going to use this again. hopefully you'll get some idea. But this is called a determinant of a matrix. And so you take the three components, I, J, and K, and then you put the components of the velocity vector in the next row, and you put the components of the unit vector in the next row. And the process of finding a determinant, which is like a 3 by 3 matrix, starts off as a 3 by 3 matrix. The resulting math says you take the I vector, and then you, this is just, I'm going to write out the result and explain it. Like I said, you can, if you take calculus-based physics, you'll know what this means. But what you end up with is a vector, and that this vector is the direction of the magnetic field. And this is just an easy way to remember how to come up with the equation. But ultimately, it's just a mathematical way of looking at the right-hand rule. If you have two vectors, the cases that we're looking at in this class most of the time is where the velocity vector would be going this way, and say the position vector goes this way, and the magnetic field, which is going to be out here, is probably going to go that way. It's going to be perpendicular to both the direction of the moving charged particle and the direction of the vector from the charged particle to the point in space. So that this is going in this direction. This is going this direction. The magnetic field is going to be going in that direction or that direction. I'm not sure which one it is, but it's perpendicular. Now, if you go to some place where this is not perpendicular to the velocity vector, then it's a little more complicated mathematically. But it's, you know, if it turns out that if you took this vector, the velocity vector, and you wanted to see what the magnetic field right along the path is, you'd find out it's zero, because when you do this, what's called a cross product, the cross product of two vectors that are parallel to each other is zero. So there is no magnetic field anywhere along the path of the charged particle. The maximum magnetic field is going to be perpendicular to the moving charged particle's direction. And the closer you get, is the higher the magnetic field is. It's kind of like with our magnet. You know, we measured the magnetic field around a magnet, and we saw, you know, how in the center that it was symmetric, and therefore we didn't have any, you know, components in that direction. So it's kind of the same, somewhat the same situation. So what do I want you to maybe get out of this thing is that the equation for the magnetic field strength is very similar to the equation for the electric field strength. The big difference, if you compare the two equations, is we have this different constant. Instead of K, we have mu0 over 4 pi. Secondly, we still have the charge, which was in the electric field equation. We still have r squared, the distance between the charged particle and the point in space, but we have this additional term, which is the velocity. And instead of going in the direction of the velocity, the magnetic field is perpendicular to the velocity, but also perpendicular to the vector that goes from the charged particle to the point in space. So it's a little more complicated, but there's a lot of similarity between the two. That's why I wanted to bring it up. Okay. Yeah. Yeah, so it is supposed to be negative. If you ever take linear algebra, you'll find out that to take the determinant of this matrix, which comes out to be, if it's just a matrix, it comes out to be a single number, and the way it works is the sign depends upon where you are in the matrix. So it's when it's here it's plus, when here it's minus, when here it's plus. So it is supposed to be negative. So let me just kind of explain. I'm just going to show you one thing. The way it works, the first term is you take this number, you take I, the unit vector in the I direction, in the X direction, and you block out this column and this row. And what you're left with is this kind of, it's called a, yeah, what is it? It's got a certain name to it. It's not a cofactor, but it's anyway, it has a special name. And then what you do is you take this times this, so you do this cross product. So you take this times that, and you subtract this times that. And that's why you get V sub y times R sub z minus B sub z times R sub y. That's where the negative comes from, is this, when you multiply these in this diagonal it's positive. But yeah, so it is all mathematically based. There is a mathematical way of doing the right-hand rule. You're not going to have to worry about that for most everybody. Now, the next one, and this is in your textbooks if you want to go back and look at it if you're more interested in it, but I'm just trying to give you some general ideas. The next thing that they do is they look at a current carrying conductor. So what you have is a little segment of wire. So instead of a charged particle, you have a moving charged particles inside of a wire. You have the basic same information. Instead of the velocity vector, you have a vector associated with the direction of the current. You still have a unit vector that goes from this differential piece of wire, dl, to a point in space. So this is the unit vector, this is the actual position vector. The difference between this and the charged particle is you actually have a wire which consists of a lot of little dLs. You know, if you have a wire, what they're doing, so this is my wire, what they're doing is they're taking a really small part of the wire and they're analyzing that. But if you want to figure out what the total effect of the entire wire is on the magnetic field at some point P in space, you've got to add all those little differential things up, which means you have to integrate. So if I look at the equation for the moving wire, you get this equation. So instead of the magnetic field, it has this D magnetic field. So this is my differential, just like we were talking about in calculus today. So, you know, we have a differential amount of magnetic field. If we want to actually figure out the total magnetic field, we have to integrate it. You still have this constant mu0 divided by 4 pi. Instead of velocity, you have the current. This is a scalar, but the way you show the direction is this little dl. So this is a differential length, and it has a direction to it. So that's how you figure out what the direction of the current is moving. Not by the current is not a vector, but the position of the little differential element has a vector form to it. And then you do this cross product, which we just talked about, with the unit vector between this differential element and the cross product between the differential element and the unit vector from the point, the dl, to the point in space, and you divide by the scalar, which is the distance from the element to the point in space. So to get the total magnetic field, you'd have to integrate it. And in calculus-based physics, we'll do something like that, but for you guys, we're not going to do that. Okay? So that's kind of my introduction. The similarities between electricity and magnetism, you can actually show mathematically. So now we're going to go to something that's fairly straightforward, and then we'll divert into something that's a little more complicated. So what we're going to do is we're going to look at what is the magnetic field around a wire. Okay, we're not going to worry about a charged particle. There's not too many charged particles that we deal with on a practical basis. So what we have is we have a wire And what I'm going to do is, instead of showing the wire in its length, I'm going to show it in its cross section. So what we have is we have current flowing through this wire. I guess what I'll do is I'll kind of draw a little dashed line. So pretend this is the wire moving. But what we're really doing is we're looking at the wire like that. Instead of looking at it like this, we're looking at it straight down the wire. And the question is, what is the magnetic field around this wire? And what does it look like? And what is the magnitude? You would think that the magnetic field is stronger closer to the wire. I should have something that's round, but I don't. So just pretend this is round. So you think the closer to the wire you are, the greater the magnetic field. Also, you'd figure that the higher the current through the wire, the greater the magnetic field. And you would be right, okay? So I'm going to draw the magnetic field around this wire. And I'm going to erase those little dashed lines for right now because I want you to think you're looking right down. So the magnetic field lines around a wire look like this. They're just circles. And they have a direction. And you figure out the direction based upon the direction of the current and the right-hand rule. And I may have done it the wrong way. Let me see if I can make sure I know how to remember how to do this. Put your fingers in the direction of the current. And what am I doing here? Yeah, I think I did them the wrong way. So if you take your hands and wrap it in the direction of the magnetic field, your thumb should go in the direction of the current. And I'm showing the current going into the board because I've got so if it was going into the board, it would actually, I got to change them around the other direction. So I just arbitrarily drew the arrows, but not thinking about it. So this is current into board. So if the current's coming out of the board, you curl your fingers that way and your thumb would go like that. So that's telling you the direction of the current. Now, as far as the magnitude, what is the magnetic field? Well, it's a function of radius. It's going to be constant at a given radius. The magnetic field will be constant. And it's equal to mu zero, this constant we just talked about, times the current divided by 2 pi times r. So mu zero is a constant which is, I can't remember what it is. I'll have to look it up. It's kind of like epsilon zero, but it's just a different constant. Okay. We'll just search for magnetic constant. That doesn't seem right. Let's look at, maybe it is right. So it's called the permeability, vacuum permeability, permeability to free space. That's the one I remember. And mu zero is equal to 4 pi times 10 to the minus 7th, which is 1.256 times 10 to the minus 6. So let's write it out as 4 pi times 10 to the minus 7th. And we can figure out the units in a second. Well, r is the radius, which is the distance from the wire to the point in space, and that's in meters. And I is the current, and that's in amperes, and pi is pi, and 2 is 2. Okay. So it's a pretty simple expression, mu 0 I over 2 pi r. So as you go out further away from the wire, the magnitude goes down. If the current increases, the magnetic field strength increases. So that's the first situation. So that actually leads me to another it's called Ampere's law. And what Ampere's law is, it's one of the fundamental laws of electromagnetism. So we talked about, if you watch the video, because it was a snow day, but in the video we talked about something called Gauss's law, which related the electric field around a charged particle to the charge that was inside this sphere, this three-dimensional sphere that encloses the charged particle. So that said the electric field that was equal to something to do with the charge divided by epsilon 0, I think, if I remember correctly. Ampere's law, what Ampere's law does is it relates current to magnetic field. So let me just find it because I didn't bring my book and I want to make sure I get it right. So we'll search for Ampere's law. Yeah, those are more complicated than I wanted to have. Let's go back here. Let's try that one. Yeah, that still looks pretty complicated. Yeah, it's too much heavy math. Well, I can find it in my, I'm going to open up another smartboard thing here because I've got it somewhere. We'll go to chapter 19, I think. So that, you saw this daunting looking equations. So if you ever take a class in physics in electromagnetism, then you end up looking at this in a much more mathematical format, which can be challenging from a math perspective. And that's why people can find this subject very difficult. So what I'm trying to do is to give you kind of a general feel for what is going on here. So I'm sure I've got Ampere's law here. Okay, so there's Gauss's law. Yeah, so let me just use this. So Gauss's law says if you integrate the electric field over a particular area, and this is what's called a surface integral. You're taking this electric field and it's piercing this three-dimensional surface, and you add up all those, and the dot tells you you're taking the component that's perpendicular to the surface. And that's equal to the charge enclosed by that three-dimensional surface divided by epsilon 0, which is related, it's just equal to 1 over 4 pi k, where k is Coulomb's constant. And you can use Gauss's law to derive Coulomb's law. And you can also use it to calculate the electric field outside a charged sphere. And you can also use it to calculate the electric field between parallel oppositely charged plates, a capacitor. So that's the practicality of Gauss's law Notice it involves vectors again, but we're not going to talk about that. Now, this is Ampere's law. So so if you look down here, here is a wire. Okay, so here's my wire. It's pointing in towards the board, and I want to know what the magnetic field is at. Well, what I wanted, I've got this line. It's not a surface. It's just a line that goes around the wire. So you can think of that as a piece of wire or a hoop or a loop or something like that. And along this loop, you have these differential length elements, which have both a length and a direction. So this one's pointing kind of up to the left. This one would be pointing to the left. This one would be pointing down. This one would be pointing to the right. So these little length elements are vectors. And what you do is if you take the magnetic field at this particular point in space, and the magnetic field is going to, in this case, is going to have a direction like that. So there's going to be a magnetic field at that point, and you do this dot product, and because the direction of dl, if we have a circular hoop, the direction of B and delta L or dl are in the same direction. So this ends up just being a product instead of this dot product. If you add up all those products of the magnetic field and the differential length elements, that's the left-hand side. And that should be equal to this constant mu0, which we just introduced, times the current through the wire. So it kind of has similarities between the Gauss's law said we had this charged particle inside a sphere, and we did a surface integral to sum up all these electric fields. For Ampere's law, we take what's called a line integral. So if we wanted to apply, so here's my wire. If I wanted to apply Ampere's law to this, I'd put not a surface, but a line around it. Think of my fingers as having infinitely small thickness. And if I add up all the magnetic fields dotted with the differential length elements that around that loop, then that's equal to the current through the wire, which is inside this loop, times mu0. Now if I didn't use a circular loop, I used some kind of non-circular loop, then these would not be in the same direction. But if I integrated them, I'd still get mu0 times I. We just choose a circular loop usually because it's easier to deal with. But this equation applies. And so you can see that for the case of this wire and looking at a certain distance, that if I integrate the length around this, if I integrate these differential lengths around this loop, it's just going to be the circumference of the loop. And so for our special case that we were just looking at, if you apply Ampere's law, you get, on the left-hand side, you get B, which is constant at a constant radius, times the circumference, which is 2 pi r. And on the right-hand side, you have this mu0 times I. So if you want to solve for the magnetic field strength, it's just mu0 I over 2 pi r, which is what I told you. That was the equation I gave you, and that's where it comes from, using Ampere's law. What are you going to be responsible for using this equation? Okay, just plugging in the numbers. It's pretty simple. Okay, so that is kind of the simplest situation. Let's add a page. So the next more complicated is what is the magnetic field inside a coil? I guess the first thing is, what is a coil? Before we answer that, right? Coil, Well, a coil is just a loop of wire that is looped around multiple times. But it's confined to a fairly small thickness. So we just take wire and we loop it around. And I'm going to go grab one for you. So hold on, I'm going to bring a coil in and just show you what it looks like. I am coming back. Okay, so I'm going to hand one of these around. So here's one. Here's one. I'm going to show you this one. Did I turn my microphone? I don't hear my microphone. Maybe I never turned it on. Oh, I never did turn the thing on. Okay. So anyway, this is a coil. So what it is just individual pieces of wire that are wrapped in a loop. And so if I just did one wire, that would be a coil of one loop. If I do it multiple times, then I get one that has multiple loops. And you can see it says 200 turns. So there are 200 loops of wire, which is going to be a lot of wire if you stretch it out straight. And what you can do is you can apply Ampere's law to this configuration as well. And what we do is you can only apply it to the center. So this is what is the magnetic field strength in the center of the loop. And what is the direction of the magnetic field? Well, it depends upon which way the current's going, whether it's going this way or that way. There's another right-hand rule that associates the direction of the current and the direction of the magnetic field, which we'll talk about in the lab. We'll demonstrate it, but just believe me right now that there is a rule that tells you which direction, how the direction of the current, either clockwise or counterclockwise, affects the direction of the magnetic field. So again, using Ampere's law, we're not actually going to do it. You can read the book if you want to see how you get the result. But so this is the magnetic field strength. This is in the center of the coil. It's equal to mu 0 times I divided by, what is it? I've forgotten what that is too. It's probably, let me open up the other lecture here because I know I've got it written down. Yeah, so here's the coil. So you've got the wire coming in. You create this magnetic field, and they all kind of add together. So each one of these, in each little segment, creates some magnetic field here at the strength. And if you have a single loop, the magnetic field strength is equal to mu 0 times I divided by 2R. So you don't have the pi in there, it's just 2R, where R is the distance from the center of the coil to the edge of the coil. So this would be R, capital R. And that's for a single loop of wire. But if you have n loops of wire, then the magnetic field strength is equal to n times mu 0 times I over 2R. So that, it's directly proportional to the number of loops. Each loop's going to contribute to the magnetic field at the center. And each part of each loop contributes to the magnetic field at the center. It's a way to generate a higher magnetic field than just a single wire, because you're building upon all these different, adding all these loops up together. And notice that my drawing says there's insulation. You have to have insulation around each one of the wires. If you just have one single wire, then you can't. What would happen is you'd end up with more current, but so you always have to insulate them. So the magnetic field that we're calculating has has units of Tesla. The current has units of amps, which are coulombs per second. R is the radius of the loop. So that's the distance from the center to the outside. That's in units of meters. So we got the magnetic field around a wire, and we've got the magnetic field inside the center of the loop. Now you may ask the question, well, what about the magnetic field strength here? It's not an easy calculation because you can't use the symmetry. Here you can use symmetry because everything's equally spaced, but if you move it here, it's not, you probably have to use that equation that we had earlier, and the problem becomes much more difficult. So that, the one advantage of a loop like this is you do get a stronger magnetic field in the center. The difficulty is that the magnetic field is not constant as you move within the loop. And the third situation we have is a solenoid. So that's what this is. So I brought this, you can hand this around. I only brought two of them in, I guess. So it looks like a coil, except the wire is spread, it actually has a thickness, a distance to it. Here, yeah, it does have an X distance, but it's pretty small relative to the radius. Whereas this one, the radius is reasonably small and the length is bigger than the radius. Okay. You still have multiple loops to try to increase the magnetic field strength within the solenoid. And instead of having, in the case of a coil, we are looking at the number of turns. N is the number of turns. We also have the number of turns here, but the important quantity in calculating the magnetic field inside a solenoid is not the number of turns, but the number of turns per length of the solenoid. So N, small n, is the number of turns per length, which is just the total number of turns divided by the length over that of the solenoid. And the magnetic field strength inside the solenoid is mu0 times N, the number of turns per length, times the current. You'll notice there's no R involved. So here, there's an R involved. Here, you're calculating the magnetic field strength at the center of the loop. Here, for a solenoid, if the radius of the solenoid, this distance, is small relative to the length of the solenoid, the magnetic field inside the solenoid is constant. So it doesn't matter where you are inside. It doesn't matter whether you're, for an ideal solenoid, the magnetic field is constant in this direction, and it's also constant across the inside. But defining the parts again, B is the magnetic field strength in Tesla. Mu is the permeability of free space, which is 4 pi times 10 to the minus 7th. I is the current in amps. Numbers n, small n is the number of turns per unit length, which is just the number of turns divided by the length. Okay, so those are the three main things that we're going to look at as far as how you can relate current flowing in a wire to the magnetic field associated with it. So we've got a wire, we've got a coil, and we've got a solenoid. Now the solenoid, you can get a really big magnetic field in there. But like I said, the other big thing about a solenoid is that it's uniform across the solenoid. And you can prove that using Ampere's law again. So all of these can be derived using Ampere's law. Okay. So that's it for chapter 20. Chapter 20 is talking about, chapter 19. So chapter 19 covered the forces on moving charges and also the magnetic fields associated with moving charges. Now we're going to start in chapter 20. So let me assign chapter 19 homework. By the way, next Friday's the physics test on up to chapter 19, so it's 17 and 18. Maybe I will actually include some 19. Yeah, let's do that. So the next test will include chapter 19 as well. So plan on having your homework done by Wednesday for chapter 19. And so we'll have 17, 18, and 19 on the test, which will be next Friday. I'll put together a review video. And there'll also be a take-home part, which we'll be using Kirchhoff's laws. Okay, chapter 20. So what we've just talked about in chapter 19 was a moving charge creates a magnetic field. We talked about how the nitty-gritty details using those vector equations. We introduced Ampere's law, which is a more global perspective, and you can use Ampere's law to then calculate the magnetic field around a wire, a coil, and a solenoid. Now what chapter 20 does is it talks about what happens if you have a changing magnetic field. So here we had a moving charge to create a magnetic field. What if we have a changing magnetic field? What's that going to do for us? Okay, so this guy named Michael Faraday was trying this experiment out, and what he had was a circuit, and the circuit consisted of a battery. It consisted of a coil like a solenoid, so like this, and then there was another solenoid on the other side. So there's no direct electrical connection between those two solenoids. So has everybody watched it? Let me get the other solenoid so I can use that as a prop. Okay, so what Faraday knew at the time when he was doing these experiments was that if I run current through the solenoid, that I can create a magnetic field. So he knew that much. If I wanted to, I could make an electromagnet by putting this coil right here. And so he thought that if I put another coil near it and I run a current through this circuit and create a magnetic field, does this magnetic field over here interact with this solenoid to create a magnetic field over here, or something to happen? So when he ran the experiment, he closed the switch and he looked over here to see if there's any current flowing through the secondary wire, and nothing happened. So he closed the switch, looked at his gauge, zippo. Then he opened the switch. Now he's not looking when he's opening and closing the switch. He's looking at, he's like, okay, let me close the switch. Okay, what happened? Nothing. Okay, I'm opening the switch. Let me look. Oh. Then he got some guy to help him out. He says, hey, you close the switch and I'll see what happens. So in the process of closing the switch, he saw a spike in the current. And then when he opened the switch, he saw a spike in the current. So what happened was he was creating a current in the secondary circuit, not when the current was flowing, but when it went from zero current to the current, or from current to zero current. It happened because he was changing the current, and that also resulted in the magnetic field in the solenoid changing. So he came up with this law, Faraday's law, which related the change in the magnetic field from the primary circuit induced a voltage in the secondary circuit. So I don't know if I've got Faraday's law here. Yep, so there you go. So the whole idea is you can create or induce a voltage from a changing magnetic field. And the relationship is this epsilon, which is this electromotive force. So if you remember back when we talked about batteries, we said batteries were a source of an electromotive force. The electromotive force was a volt, it was measured in volts, But it was basically the electromotive force was the source of a voltage difference. Batteries, Van de Graaff generators. Now he found out there's another source of voltage, and that source is from a changing magnetic field. And the equation turns out to be real simple. It's equal to negative N, which are the number of loops in the coil, times the derivative of the magnetic flux. Okay, I'll define magnetic flux here in a second, but it's related to magnetic field. The derivative of the magnetic flux with respect to time. So the more loops you have here, say in the secondary coil, the more loops you have, the higher the voltage you would induce or generate. And the quicker you change the voltage, to change the current, which would change the magnetic field, which would change the magnetic flux, the quicker you change the field, the higher the voltage that you generate. So when he ran the experiment and he had the switch closed, the magnetic field was constant, and therefore it didn't induce any voltage in the secondary coil. But when he went from 0 to during that period, when you can't go immediately from 0 to some value, it's not possible. You have to go from 0 through all the values to the final magnetic field. During that period, this magnetic field was changing, and it was changing quickly, and that's why he would get a spike in his current. But once it reached equilibrium quickly, there was no change, therefore there was no induced voltage, and he didn't see anything. But then when he opened it, the magnetic field went from being in the coil to there being no magnetic field, and so there was a change. So when he opened it, the current went one way, and when he closed it, the current went the other way, because the sign of the change was opposite. So that's Faraday's law, and that's the whole concept behind how we generate electricity. So what is this magnetic flux? So before we do that, we talked about electric flux, and this was, I think, in one of the videos that you watched during snow day, so hopefully you watched that. But the electric flux is just the product of the electric field times the area through which the electric field is flowing. So, let's say here's my charged particle. There's some electric field that's coming out. Here's an area. I'm just using this as a prop for area. It's nothing to do with the coil. It's just a circular area. So you have the electric field vectors going through this area. And so the electric flux is the product of the electric field vectors times the area. So the bigger the area, the more flux you have flowing through there. Just like you have a bigger pipe, you have more water flowing through it. The electric field is kind of like the flow, what the flow rate is. So the bigger pipe, the higher the flow rate, the more stuff flows through this cross section. So that's electric flux, and the magnetic flux is the same thing. If I had something generating a magnetic field and I had an area, the magnetic flux would be the magnetic field times the area. So you can increase the flux by either increasing the magnetic field or by making the area bigger with the same magnetic field. And then this sign is associated with the angle. So if I have this area oriented like this, it's not going to go through there because it's just going to hit the side. Whereas if this is going to give you the maximum amount, and the amount that goes through the hole here is dependent upon the angle. So you can go from 0 flowing through. It doesn't go like this. It just flies on by. It never goes through. And it's dependent upon the sign of the angle between the area that I'm looking at and the direction of the flux of the field of vectors. So they're essentially the same kind of thing. And that's what you're looking at here. How much does the flux change? So you can change the flux by changing the magnetic field strength, or you can do it by changing the area, or you can do it by changing the orientation. So let's say here, now I do have a coil, and you have some kind of magnetic field that's happening going in this direction. So how could I change the flux through there? I could change the magnetic field could oscillate and just have this stationary. So that would be one way. The other way would be to take this and squeeze it down or spread it out to change the area, which I can't because it's rigid. But if you had a flexible wire, you could change the area. The other way is you could rotate it. So I could go from maximum flux here to zero flux there, and the faster I do it, the quicker it changes. And that's how a generator works in generating electricity. You're actually rotating this coil, and you're varying the area through which the flux goes. So you're keeping this geometry fixed. You're keeping the magnetic field fixed. You're changing the flux by, instead of switching the thing on and off, you're changing the flux by rotating this coil. And that's what a generator is. As you rotate this coil in the presence of a magnetic field, it generates a voltage in the coil. And then that voltage is then shipped to us via power lines. And the thing is that the voltage is alternating. You know, it's going to go, the amount, how this thing area changes as you rotate it is a sinusoidal function of time. So you get a sinusoidal voltage. That's what we get out of our power lines. But it's rotating, you know, it's rotating at 60 times per second, or at least it's. So you control the frequency of the power that's being delivered to us by the people who are generating the power and how quickly the generator is rotating. So 3,600 revolutions per minute, or 60 revolutions per second. In Europe, they're doing it 50 times per second instead of 60 times per second. But that's all based on Faraday's law, which he discovered using this particular experiment. So everything we have, all of our modern conveniences and anything that has to do with electricity, is a result of this particular discovery, applying this particular discovery. Otherwise, we'd have to do everything off batteries, which would be not so good. We wouldn't be doing what we're doing. Okay. And the last thing we're going to talk about today, and we'll, again, on Wednesday next week, we'll practice this. This is the question of, depending upon which way the current's flowing in this loop, what does the magnetic field look like? Does it go like this around the loop, or does it go around the loop? And it's Lenz's law. No, that's a different one. This is so that's the right-hand rule. Lenz's law has to do with how does the change in the magnetic field affect which direction the current flows in the wire. So what will happen is this thing rotates in the presence of a magnetic field. The current will go one direction, and then it will go the other direction, and it will oscillate. And the Lenz's law is a way of figuring out which, based upon how things are changing, which direction the current is induced in the loop due to this changing magnetic flux. I think that's what it says. Direction of the current in the loop is such that it tries to maintain the magnetic field strength before the change is made. Okay, I know you don't want to know what that means, so we're going to try to do some demonstrations next Wednesday to help you understand that particular concept. Okay, so that's it. So Chapter 19 homework due next Friday. The test will include Chapter 19, 17, 18, and 19. I'll put a review together at the beginning of the week.